about is the view of chromatography from outside the column, sort of a macroscopic view of chromatography. And today and for the next several weeks, we're going to be looking at a much more microscopic view of chromatography, and that is what's happening inside the column. And this is not a molecular level view, it's more of a view at the, say, the particle, the stationary phase particle scale of things. But that's going to get us a long way towards understanding a lot of the processes that cause peak broadening. So today I'm going to give you an overview, a big picture of what's going on, and then as we progress through, we'll look at individual small pieces of what goes on inside the column. So today we're mainly concerned with this sort of thing, and we'll be talking about different kinds of particles and different kinds of columns, and some of the bigger elements of the factors that cause broadening. Certainly on Wednesday, we're going to get pretty far into a discussion of diffusion, which is a molecular level process. And we'll have to look at some equations that describe diffusion and talk a little bit about the underlying physics involved in diffusion. I decided I wanted to make a list of all of the different things I could think of that would cause broadening in a chromatographic column. And I came up with this 3 pages long list. We sort of spoke about some, but not all, of these issues last week when we were talking about the overload issue. One thing we didn't talk about is a process called viscous fingering, which is very complicated, and we'll get to it sometime down the road, specifically when we get into liquid chromatography, because it's not involved in gas chromatography. I wanted to list all of the different physical variables that relate to broadening, and you almost can't think of something that's not related to broadening. There's geometrical issues. The diameter of the column does matter to a certain extent. Much more important is the particle diameter, which is a very critical variable in determining how many plates you're going to have. The porosity of the bed as a whole, if it's a packed bed column, is important. And then the porosity of the particle, whether it's a fully porous particle or a non-fully porous particle, or if it's a non-porous particle, are all very different types of particles, and the band broadening will vary from type of particle to type of particle. Physical factors: the flow rate that you operate the column at, the column temperature, solute properties, especially its retention factor, and its diffusion coefficient in the mobile and stationary phase, all important issues. For certain kinds of solutes, what we call their secondary sorption characteristics can be responsible for a lot of peak broadening, and we'll talk about this specifically when we get into the case of liquid chromatography. Various properties of the mobile phase are very important. The viscosity of the mobile phase is super important. The viscosity is what differentiates gas chromatography from liquid chromatography, and hugely impacts how we actually build our instruments. Whether the mobile phase is able to block secondary sorption sites on the stationary phase is a very important issue. And we'll talk about that in a lot more detail when we get into liquid chromatography. So that's sort of a big picture of what we're going to talk about today and for the next couple of weeks. So, with that, let me get into the subject. There's a very important property of a column, which depends upon a lot of those variables that I just mentioned, called its HETP, which stands for height equivalent to a theoretical plate. And we abbreviate this as HETP or big H. And this is simply a definition. The HETP is defined as the length of the column divided by the number of plates on the column. And the way we measure the HETP is we measure the length of the column, and we measure, by whatever means we can, the width of the peak. We convert the width of the peak into the number of theoretical plates, and then we compute the HETP. Yes?
Is that ineffective, or just right? Is that ineffective, or?
If I mean ineffective, I will say ineffective. This is N, the number of theoretical plates. And that's, you can assume that I'm talking about the number of theoretical plates unless I specifically say the number of effective plates. Okay, I will not violate that. Okay, now, what does N, or another related issue is, what does H depend upon? And one of the first things people found out that it depended upon was the flow rate or the linear velocity of the mobile phase. And one of the earliest equations used to describe the HETP had the following form. Big A is a constant, big B is a constant, the velocity U, that's the velocity of the mobile phase as it moves through the column. If you want, you could substitute the flow rate for a given column. You could substitute the flow rate for the velocity if you wanted to. Plus C, another constant, times the velocity. Now, the first people to come up with an equation of this form was led by a fellow by the name of Van Deemter. And this equation is invariably known as the Van Deemter equation. The three people involved were Van Deemter, Klinkenberg, and Zwijderweg. And so if you ever publish a paper, you want your name to be first or have the most pronounceable name. But no one, to my knowledge, has ever called this the Van Deemter, Zwijderweg, and Klinkenberg equation. Okay, so what does this equation tell us about the HETP as a function of velocity? Well, let's plot it up. I don't know why it's doing that. Here's what the thing looks like when you plot it. Here's the HETP on the vertical axis, and here's the flow rate or the linear velocity on the horizontal axis. And here's the whole curve. That's the Van Deemter plot for this column. The A, B, and C are empirical constants. You have to measure the plot, and then you can, from fitting the curve one way or another, determine the constants A, B, and C. The three parts of it, the A plus B over U plus CU, the three parts are, A is just a constant. Here's the A term. here's the C term of the velocity. And the B term has an inverse dependence on velocity. So here's the B term. If you have a good-looking Van Deemter plot, and if it in fact does become taken to a high enough velocity, become pretty much a linear function of velocity, or you can, to get the A and the C, you can just lay a ruler on that and extrapolate the curve back to zero velocity, and that'll give you a pretty good approximation of the A term. The C number is simply the slope of that straight line, the slope at high velocity. And then you can get the B term by subtracting A and CU from H. And that leaves you B over U. And then you can take a couple of your data points, say there and there. You would take them at the lowest velocities you can get to. And then by solving this equation, you would come up with your B term. The most important characteristic of this curve is that there's a velocity at which the HETP goes through a minimum. If we start at really low velocity, say way out here, and we make the velocity bigger and bigger and bigger and bigger, the H gets smaller and smaller and smaller and smaller, goes through a minimum, and then as we continue to increase the velocity or the flow rate even more, it swings up and eventually becomes a straight line. The reason the minimum H is important is that it will give you the maximum value of N that you can get on that column. So for a given column, if you want to get the largest number of plates, you need to be working at this velocity here, which minimizes the HETP. So there's an optimum velocity. Now, the way people normally do their business, do their work, is they take a few points on the curve, 5, 6, 7 points on the curve, and then they fit the curve to the Van Deemter equation. And then you have a little least squares program, a multivariable least squares program, but it's still nonetheless least squares program. And it calculates for you the fitting coefficients A, B, and C. And so you have your numbers for A, B, and C. If you want to find the optimum velocity, you set the derivative of the HETP with respect to the velocity equal to 0. That's comes straight out of Calculus 1, maybe week 2. And you set the slope equal to 0. The slope, of course, is a minimum at either the slope is 0 or at either a minimum or a maximum in the curve. Well, if we differentiate this, the derivative of A, a constant with respect to velocity, is nothing. The derivative of B over U with respect to velocity is minus B over U squared. And the derivative of CU with respect to velocity is simply C, and we set that equal to 0. And so U is equal to the square root of B over C. That's my optimum velocity. This is the velocity you want to work at if you want to produce the maximum number of plates for that column. You can calculate the minimum plate height by taking this velocity and sticking it in there and sticking it in there and crunch through the algebra and you'll find out that the minimum plate height is equal to A, the constant term of the Van Deemter, plus 2 times the square root of B times C. Since we want the minimum plate height to be small, because that will, the smaller we can make the minimum plate height, the more plates we're going to have on a column of a given length. We obviously want to work with columns with small a values, small b values, and small c values. So there's no problem, there's no untoward consequence of working with a column with a small a or a column with a small b. But if you work with a column with a small c, since c is in the denominator over here, that makes the optimum velocity get bigger. Well, let's think about this for a minute. Do I want a system that has a high optimum velocity or a low optimum velocity? Which is better? Even though you can have the same value of h min, which would you prefer? One which has a high optimum velocity or a low optimum velocity?
High.
Why?
Then I don't have to wait so long for
That's
separation.
exactly right. You want this to be small, you want this to be small, and you want that to be small. That will get you the most plates for a given size column, and it will let you get that analysis done in the least period of time. So A, B, and C are your enemy. Now let's look at, this is the results of some real calculations. This happens to be done for a GC capillary column. For those of you who've never used a capillary GC column, it's a very, very, very narrow, hence capillary, tube where the stationary phase is coated on the wall, the inside wall of the tube. So it's not packed with particles at all. So here's the h, and here's the linear velocity. And there's 3 plots here. One is for a capillary that's 500 microns in diameter. That 500 microns is 1/2 of a millimeter. This is for 200 micron ID capillary, and this is for a 50 micron ID capillary. I'm pretty sure that these are about the narrowest capillaries you can buy for gas chromatography. And the 500, I've seen some 530 micron capillaries, but I think that's about it. The important characteristic of this curve is that the minimum HETP gets smaller and smaller and smaller as I reduce the diameter of the column. The narrower the column is, the lower the minimum HETP is. That's number 1 difference between them. Number 2 difference between them is this slope. The high velocity slope is greater for a wide capillary. In fact, these are called macro bore capillaries. Versus a 50 micron ID capillary, and this would be called in the trade a high resolution GC capillary column. So clearly HETP does depend upon the scale of the system in gas chromatography. Okay? All sorts of the other variables that I listed will have an impact on these curves. The K prime of the solute will matter, how viscous the stationary phase will matter, how thick the stationary phase will matter. All sorts of other things kick in, but the primary variables here are the diameter of the tube and the velocity of the gas through the tube. These numbers over here are diffusion coefficients. This is a diffusion coefficient in number like 10 to the minus 5 centimeters squared per second. Diffusion coefficient in the mobile phase is a lot bigger. In fact, it's 10,000 times bigger than in the liquid phase. And this is characteristic of gases versus liquids. Gases have low viscosities and high diffusion coefficients. Liquids have high viscosities and low diffusion coefficients. And we're talking several 3-4 orders of magnitude in viscosity and 3-4 orders of magnitude in diffusion coefficients. The biggest single difference in the behavior of GC and LC comes from the viscosity of the fluid and the diffusion coefficient of the analyte in the gas fluid versus the liquid fluid. As we go through here, you'll find out that gas chromatography is a lot faster than liquid chromatography. By a lot faster, I mean a lot. Like factors of 10 and 100 times. I have seen people do GC on a time scale of 1 millisecond. The fastest LC I've ever seen is about 2 seconds. They're not great separations, but it just indicates the magnitude of the time scales involved here. This is a real Van Deemter plot, not a computed Van Deemter plot for some LC particles. These were adjuvant XDB columns. XDB is a type of chemical bonding that they use in making attaching the stationary phase to the underlying particle. And the particle is a silica particle. And the data here were for particles that were 1.7 microns. I said 50 microns was the narrowest capillary you'd see in GC. This is 25 times smaller than that. 3.5 micron particles and 5 micron particles. This was the standard of the LC industry 10 years ago. About 5 years ago, this was the standard particle. This particle now is what's used in what we call UPLC, or ultra-high pressure liquid chromatography. What's the difference? The difference is that the minimum HETP went from there to there to there. The slope went down to where it almost looks flat. It's not. There is a minimum in this curve, and then it does come up, but it comes up very slowly. The slope of the 1.7s are definitely smaller than the slope of the 3.5 micron particles. The optimum velocity is distinctly higher for the 1.7 micron particles than for the 3.5, than for the 5 micron particles. And a few minutes ago, we concluded that you wanted the optimum velocity to be high because it gets the analysis done quicker. So clearly there's been a significant improvement in performance of HPLC columns as the particles were made smaller. A rational question is, why did it take them 10 years to get from here to there? The answer is that the pressure drop on the column goes pretty closely with the square of the diameter of the particles. As you make the particles smaller, the required pressure drop gets higher and higher. This column works perfectly well with a 400 bar system, and this thing needs a 1,000 bar system to make it work. And a pump that can not leak fluid when you apply 1,000 bar to it is a lot harder to make than a pump that only has to handle 400 bar. And that's the bottom line why it's taken that long. It took us 20 years to get from 10 micron particles to 5 micron particles. Here's an analogous plot for packed bed GC. This is not an open tube GC. This is say a 1/4 inch ID tube packed with particles, and then the stationary phase is impregnated into the particles, and then those particles are somehow gotten into the column. And that's a real art. The particles are the same in all of these curves. They're the same mesh, same diameter, same porosity. They're the same particles, but they're coated with different percent by weight of stationary phase. So this one has 50% by weight of the particle is stationary phase. And then less and less and less. And so down here, it's only 18% by weight stationary phase liquid. The rest of it is the solid support particle. Since the particles are the same, the surface areas of the particles are the same, but if the amount of stationary phase is greater here, then this is on average a thicker film of stationary phase in the particles. Clearly, as we make the stationary phase thinner and thinner and thinner, the slope goes down, that the minimum HETP improves dramatically, and the optimum velocity moves out to higher values, which is where we want to go. Clearly, the stationary phase loading, the percent by weight of stationary phase, is an important parameter in gas chromatography. There's a trade-off between this and this. And the trade-off, obviously this is better, but since the chemistry is the same, the retention factors here are going to be a lot higher than the retention factors on the 18%. What that means is that you can inject a larger sample onto the 50% loaded particles than onto the 18%. So they don't overload as easily when you've got more stationary phase. Now, I put this slide in because it illustrates an important point. This is not a linear function, not a very linear function of the velocity, and this is not a very linear function of the velocity. The Van Deemter equation is simply an approximation. It's not like the first and second laws of thermodynamics. But, you know, you shouldn't hold your breath while you wait for a violation of those laws. Here, I always like seeing a straight line because I say, oh, it worked again. It's nice to see one every now and then. There's an awful lot of reasons why we have deviations from exact fitting of the Van Deemter equation. This happens to be for gas chromatography, but we see deviations also in liquid chromatography. Okay. So the two primary variables when we're thinking about the relationship between HETP and speed, velocity, are H and the velocity. H has units of length, and velocity has units of length per time. So I can say that this way. This is L, and this is L per T. These are dimensioned quantities. It turns out that it's actually much more useful, both theoretically and for practical purposes, to work with what are called dimensionless coordinates. And John Knox was really the first person some 40 years ago to think of chromatography in terms of these reduced variables. The reduced variable for HETP is always written as a little h. If you're dealing with a column that is packed with particles, little h is defined as the HETP relative to the particle diameter. Particle diameter has units of length. HETP has units of length. So the reduced plate height is dimensionless. The reduced velocity, which is always written as a Greek nu, again, for a column that's packed with particles, this reduced velocity is defined as the velocity times the particle diameter divided by the diffusion coefficient of the solute in the mobile phase. Big D sub m. Now, velocity has units of length per unit time. Particle diameter has units of length. So the numerator has units of length squared per time, which is very nice because the units of diffusion coefficients are length squared per unit time. So you typically see them cited in centimeters squared per second. By chemist type people. But the engineers, of course, want to be different. So you'll frequently see them in all, if you're in the engineering literature, in meters squared per second. Just be happy it's not in feet per minute, okay? Excuse me, square feet per minute. And so we have a difference of 10 to the 4 in these quantities, depending upon the units. But taking the units into account, the reduced velocity is a dimensionless quantity. Now, I love this plot. This data is the same as that data. All that was done was to change the coordinate system from HETP in centimeters and velocity in centimeters per second over to the dimensionless system. And the magic is that the three curves virtually blend together. So if I were to fit the three curves, fit them individually to the Van Dienter equation, what I'd find is that the A would equal to A would equal to A, the B would equal to B would equal to B, and the C would equal to C would equal to C in dimensionless coordinate system. So there's less to remember. And here's the magic. That's about the minimum reduced plate height for all three kinds of particles. And that's close enough to 2 to not need to remember 1.85. It's not going to make any difference. So if someone asks you, hey, what's the best HETP I can get on these particles? All you have to do is say, what size particles are they? And you double it. And that's the best HETP you can typically get. If you want to know what's the best velocity to run at, all three of these, somewhere between 6 and 8, it's close enough to 10 to say, who cares? Okay? So your best reduced velocity is something a little bit less than 10. Now, to calculate the actual velocity, you need to know the particle size and you need to know the diffusion coefficient. But 2 and 10 are not hard to remember. and you look like a magician when you can give the answers to the questions. That's the practical reason for understanding why we like to use these reduced coordinates. There are good theoretical reasons for why this works, why it is u times dp over dm, but we got to get more into the theory side than into the practical side to get there. Now, so far I haven't told you a darn thing about where A, B, and C come from, except they're somehow related to the particle size and the velocity and viscosity and diffusion and whatnot. But I haven't attached a physical meaning to A, B, or C. One of the processes that we believe is very important in establishing the HETP is the transfer of the solute between phases, from the mobile phase to the stationary phase, through the stationary phase, back out of the stationary phase into the mobile phase. Because as the solute molecules are going down the column, they are continually adsorbing and desorbing many, 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 many times. And the speed with which they can adsorb and desorb is related to the kinetics of the mass transfer process between phases. The reason that should influence the peak width is shown in this cartoon. Suppose we took a sample, shot it in the column, let it go in the column, and then turn off the flow. And let the solute come to equilibrium, perfect equilibrium, between the two phases. So if we then made a plot of concentration versus distance along the column, so this is concentration, and that's in the mobile phase, and so higher concentration in the mobile phase goes up, and concentration in the stationary phase, higher concentration in the stationary phase goes down. If we have a linear isotherm at equilibrium, then CS equals K times Cm. This is the equilibrium constant for the transfer process. So the concentration in the two phases would be exactly proportional to one another. And that would have to be the case at equilibrium at every point in the stationary phase. Now, suppose we turn the flow on. Now, by definition, the stationary phase is not flowing. It wouldn't be called stationary if it was. A very, very, very short time after the mobile phase flow is turned on, the system's no longer at equilibrium. It hasn't been given enough time to get to equilibrium. This entire mobile phase distribution has been shoved down the column a bit. The flow pushes it down the column. So this has been displaced in the x direction. And the distribution in the stationary phase is going to lag behind the distribution in the mobile phase. But as soon as the front of the peak gets downstream a little bit, the molecules in the mobile phase are going to see that there's no molecules where at equilibrium there ought to be of molecules in the stationary phase. So these guys up here in the mobile phase are going to move by diffusion down into the stationary phase and attempt to reach. Conversely, at the tail end of the peak, The molecules in the stationary phase that are lagging behind don't observe any molecules of mobile phase directly above them, and so they feel a diffusive gradient that will move them up into the mobile phase, attempting to reestablish equilibrium. The slower this process is of transfer from the mobile to the stationary and from the stationary to the mobile, the slower that is, the wider the peak is going to be when it finally comes to equilibrium again. So you want these processes to be very fast compared to movement along the column. We can call this longitudinal or axial, and we can call the perpendicular to that the transverse or radial. So you want the rate of movement radially to be fast compared to the rate of movement axially. Unfortunately, the axial motion is governed by convection, principally, whereas the radial motion is principally governed by diffusion. And diffusional processes tend to be slow. Convection can be slow or fast, depending upon how much flow you apply, how much pressure you apply to the fluid to push it through the column. But once the transverse transport becomes slow compared to the axial transport rate, you're going to get peak broadening. So that's one process. Now, if I make the flow rate higher, or if I make the linear velocity along in the axial direction higher, is this going to cause the HETP to go up or to go down? You're going to cause the peak to get wider or narrower? Going to get wider. This is the C term. Because it gets worse, it gets bigger as you increase the velocity. Okay. Now let's take a look at a packed column. I didn't have the patience to draw all those particles, so I copied this. And it's not quite exactly as I would have drawn it, but it'll do. The point is that there's no way to pack a tube uniformly with particles. The particles are not all locked in and register. They're not lined up with one another. There are gaps between particles. All of the particles are not exactly the same size. We strive to make them the same size for various reasons, especially in HPLC, but they're not exactly the same size. When a fluid moves through a bed, a randomly packed bed, the velocity, the axial velocity of the fluid is not the same everywhere in the column. So that, for instance, this flow stream here would have a different velocity than this flow stream here, which would have a different velocity than that flow stream there. Okay, now imagine that you're a molecule and you're in this flow stream, or this one, or this one. but the velocities are not all the same. The molecules are not going to come out the end of the column at the same time. Even if the molecules started at the same axial positions, if they're in flow streams that have different velocities, they're not going to come out at the same time. They could start like this, all lined up, but when they come out here, they're going to come out at different times, depending upon the relative velocities. This is a very serious problem in packed bed chromatography. And it's also a very serious problem, although it may not occur to you at this point in time, that this is a very serious problem in open tubular chromatography, even though there are no particles in open tubular chromatography. There are still velocity differences between different points in the radial points in the column. But we'll get into that later on. To a first approximation, this radial heterogeneity in the axial velocity is what's responsible for the A term. This process has a lot of different names. It depends on which literature you're reading. The most common name you'll see for it is eddy dispersion or eddy diffusion. I actually hate this second one because it makes it seem like it's a diffusive process, but it's not a diffusive process. It's a dispersive process that acts like diffusion. Diffusion causes things to spread out. Dispersion also causes things to spread out. We'll get into the B term pretty soon, but I wanted you to take a look at different kinds of particles. This is what GC particles, GC columns used to be packed with diatomaceous earth. And if you buy a packed bed GC column, this is still the stationary phase of choice. These are actually they're skeletons of an animal called a diatom, and they happen to be very porous. They have a high surface area, and they're relatively easy to work with. And GC community latched onto these in the early days, and they've never really been bettered. I mean, porous glass just doesn't do as well as does diatomaceous earth. Here's an LC particle. It's a zirconium dioxide particle made by a special process called polymer-induced colloid aggregation, which is a really neat process because it makes particles virtually monodispersive. And that's what this picture was intended to convey, that these two particles are almost exactly the same diameter, and they weren't cleaned up to be the same diameter. Here's a 1 micron marker. So these are about 2.5 to 3 microns in diameter. I'm going to skip that for the time being and skip that for the time being. Here's a neat material called a monolithic bed. This is turns out to be a silica bed. Okay? A monolith. Mono means one. Lith is Greek for rock. The entire inside of the column is one piece of silica, where all of the chunks of silica are physically unified into a single body. It's really neat stuff. This is a relatively new development in HPLC.